a very important session because whenever you're designing your study, whether it's most likely it is a hypothesis-driven study, right? And it's usually a randomized controlled trial. And what are the things that is the most crucial part of the design? First is choosing your outcome, but the second one is then you already have your intervention and who you're studying, so that's it. But the main thing is the outcome, but then after you've chosen the outcome is to get a reasonable estimate of the necessary sample size to answer your research question. And my experience with some investigators has not been very good. With others, it has been fantastic. But people that are looking at designing a study just to have the power to be able to get funding to do the study will play around so that they get a small sample size. When you're looking at these apps, when you're playing with it, you will notice that the sample size is driven mainly by the effect of the intervention. The larger the effect, the easier it is to detect it, that the smaller sample size is there. And so they say, oh, let's put the large effect size. And that is gaming the system only for the purpose of having a small sample size so that when they put in the grant proposal, it is cheaper, the funding agency will fund it. Hopefully, many times, the reviewers at the funding agency will say, that is an unrealistically high effect size. Your intervention is not going to be so dramatic. What is the minimal effect that you think is clinically important? So when I work with investigators designing their study, the sample size is not just putting one number in there and just seeing what you get. It is based on, yes, the power that you want. It's based on the level of significance, but everybody likes the magical 0.05, so there's no issue there. And it's based on how much variability you have. You're looking at the proportions of events or the number of events, and those are based on the event rate that you have. And so what you can play with is your guess as to the effect size. And people play with it or game it in such a way that they get a small enough sample size. What I tend to do is I enter into a dialogue with the investigator, and I ask them a non-statistical question. And the question is, you're doing this clinical trial to change practice. What do you think is a clinically important difference or effect that will achieve what you want to reach, that will change practice? Is it a hazard rate ratio of 1.5? Or maybe you could change practice with a 1.4, or is it a 1.3? You know your practice, you know your discipline, you can make an educated guess better than the statistician of what would be something that would change practice in your field. So typically they will say, oh yeah, we need a hazard ratio of 2. A hazard ratio of 2 was given us very small sample size of 81 per group. But what if you had gotten a 1.8 at the end of the study? You would not have the power to necessarily claim that there's got significance. But that's a very meaningful, huge effect. It could have changed practice. Now you're disappointed because you will have to say, we don't have the power, we got a non-significant result because our confidence interval is so wide around that 1.8 because of the small sample size that it includes one And so therefore I got a non-significant result. This is poor design of the study. It was designed exclusively to game the system, to get a funding agency to give you money because you were proposing a small sample size. And so what you have to be realistic, and it's unethical to design a study poorly, underpowered from an ethics standpoint, because now you've wasted however many 100 and 200 people in your study, it's time, energy, and maybe even life for something that was totally unethical because it was underpowered. So I would try to do is I game you. I say, okay, you want a 2. That's fantastic. Would you be happy if you got a 1.5? Would that change practice? Oh, yes, 1.5 would definitely change practice. Then I say, well, what about if you got a 1.2? Oh, no. 1.2, that doesn't sound like a very, it's okay. How about 1.35, halfway between 1.2 and 1.5? And now you start moving your head. Maybe. Okay, then maybe 1.3. Then you move your head more negatively. So then I say, okay, well, what 1.4? Yeah, 1.4 is fine. So then I titrate you to what I call the smallest clinically meaningful hazard rate ratio. Not using 2, not using the big one to get a small sample size. You want to get the adequate sample size necessary to address a clinically important effect. That's the ethical way to go about doing the sample size. And so these softwares allow you to do that. You have in McMaster, you start putting different ones in different columns and see, do you agree with it? Not just, oh, a sample size is good enough to get funded. That's not the purpose of doing the study. The purpose of doing the study is to have a meaningful, important study. You want to not game the system, do the sample size for gaming the system. All right, that's enough lecturing on that topic. I will not say more on that. But, all right, questions on that. What we're moving on to now is more advanced topics on survival analysis. And in your program, you have frailty models and you have joint models. So the rest of the day, lectures are going to be on frailty models and joint models. I will be presenting more the theory about it, and Vishali is going to be presenting the examples and illustrating what this means. But as I'll say, it's not very common to see, especially the joint models is something that's new. And so it's not very commonly seen in the literature. Frailty models is the first topic, and that's what I'm going to talk about now. In frailty models, the term comes about from having a given person having their what we call subject-specific hazard. And so some people are more frail than others, and so their risk of having the event is different. And so the term frailty is used for many, frailty models are used for many things, but the origin of the word frailty comes from having repeated measures of events. So I'm looking at time to recurrences of events in a given person. Came from falls in the elderly. So an elderly person may fall, get injured or not, and you want to know how can I predict time to the fall? So now the fall is the outcome. The event is time, the endpoint is the fall. Time to the event, the falling, is the outcome variable. Now, once they've fallen, hopefully maybe they had a hip replacement or not, or knee replacement, or they had some surgery or no surgery. But then now they are back to recuperated. They can fall again. They can fall again until maybe they die. Yesterday in the afternoon, we had recurrent events within a person. and you're interested in looking at time to the recurrences and the gap time, for example, Prentice, Williams, Peterson. So when they started modeling the recurrent times to events in a given person, they had, well, I can maybe say that person X is more frail than person Y. So the underlying hazard of person X is different than the underlying hazard of person Y. Maybe the other covariates are the same, but the underlying hazard in the Cox model is different. And so we have a subject-specific underlying hazard. And because it was this was first applied in elderly people and falls, they said, oh, this is a frail elderly person, this is a less frail elderly person. And that's where the term frailty models comes from. But nowadays, it's not only used for recurrent outcomes in individuals, it's also used for cluster randomized trials. And now it is for the members of the cluster share the same frailty or the same underlying hazard because they are living in the same village or because they are from the same community or they are from the same family or they are getting the intervention from this. Everybody from this hospital is getting that same intervention. You're now getting the hospital effect determines the frailty of those people that are in that hospital. So when we say frailty models, what the term applies in general to survival observations that are correlated with each other. So the repeated measures, the repeated falls in a given person are correlated. If I tend to fall because I'm more frail than Kumar, then my times to falling are more closely related to each other than his. His are more closely related to his. There may be longer times, and mine are more shorter times. So they're correlated. Mine are correlated within me. His are correlated within his. And so the survival observations are correlated within a person when we have recurrent outcomes in individuals. If I do a study where I'm randomizing groups of people, so I'm doing an intervention to give you an example of some of the ones we've done at our institute, looking at changing the size of the stents that are put in people that are having cardiac surgery. And one of the investigators said, you know, it's not problematic to have a shorter stent than a slightly longer stent. And in some hospitals, they use whatever the supplier gives them. But they're easier to put in the shorter stents than the longer stents. And she wanted to show that it's not inferior to use that. But you cannot, at the moment of working on a patient, to randomize that patient to get shorter or longer stents because they're operating. In that moment, you can't do that. In the way the operating room or the operating theaters work, they'll have a box of stents, and the physician will just say, stent, and the nurse will go get it, whatever is there. They may mix up from the boxes if they have a short one and this one. This person's been randomized to the short. They should get it from this box. This person randomized to that. Get it from that. So they said, no, let's just do for a given month. We have the boxes that are big. For the next month, the boxes are short. Then get whatever is there, but we will randomize the site again. So now we analyze the data at the patient level, but the patient's survival or outcome is now everybody in that cluster within that site during that month got the same intervention. And so now those 8 or 10 or 20 or 50 people that were operated in that hospital that month, their outcomes are correlated, maybe very small, because they have their own individual characteristics. But there is some correlation. And so that leads to correlated survival observation. Clustering then needs to take into account. How do we do it? With frailty models. And I'll explain these frailty models a little. For recurrent outcomes or cluster randomized. So here's an example of a community setting cluster design done in India. This was people with hypertension, and they had a group-based intervention done by the community health workers in 5 villages. They had 15 villages. 5 villages were randomized to get the group-based intervention. Then the other 10 villages had been randomized 1 to 2, and the usual care was in 10 villages. Yeah. So typically it's the same event. Okay? When you start doing different events, now we are in the scenario of recurrent events. And what many people do is they actually use these frailty models, but assume that a stroke is the same thing as an MI, and assume that heart failure hospitalization is just the same as an MI and a stroke. That is not necessarily true, but they say, okay, it's a cardiovascular event. And so now there are different types of cardiovascular events. So they make the assumption it's the same thing, but it's typically should be for the same type of event. So it'll be, so it's usually used more in infectious diseases. So it's like episodes of time to diarrhea, or time to the flu, or time to or malaria, or time to this, or time to whatever. And the assumption is that once you have had that event and you're treated or whatever, you go back to your original risk for that event. So once you've had diarrhea and you get treated and you're back, you're still at risk, the same risk that you had at the baseline for this. But and the same thing with falls in the elderly. It's not that easy assumption to believe is happening when you are getting these events like MI or stroke. People will argue, yes, maybe they get the MI, they're treated, and they get back to their original risk. No. Depends on what treatment you get. Many times you get the MI, you get stents put in, or you get a coronary bypass surgery. Now you're like a new person sometimes. Your risk is different. So I don't think the assumption is a good assumption, but people, for simplicity purposes, do that. And it should be, I mean, it was thought of originally for the same one, and for going back to your original state. I don't think there are methods yet that can handle when you don't go back to your original state. And that's why we mentioned what people are doing is it's multi-state models. It's the most recent thing, that the one we talked about yesterday. This is what many people are doing. But it's not yet there how to properly analyze these things. All right, so we have this study. The outcome is time to blood pressure control. So people that are hypertensive, greater than 140/90, they still be, even though they're taking medications, they're out. They're saying, if I do this group-based intervention, how long does it take you to now be in blood pressure control? Yes. No questions are done.
Anyway, in your talk proportion, you can adjust for it, right? Like you can adjust for the cluster.
How do you adjust for the cluster?
I mean, like because when you adjust, I mean, like a regression analysis, can't you adjust for based on location? Doesn't that come?
Oh, okay. So when you say adjust, you say I can put in a covariate that identifies the cluster. You can do that, but that will say that there is an effect of that cluster. So maybe you have 10 clusters, or here we have 15 clusters. So I would put 14 dummy variables in the model, right? And it just says that what is the effect of it? You're partially correct. What it's not handling is that the data are correlated. And when the data are correlated, your estimates of variances and therefore your effect sizes are wrong. What tends to happen is when you ignore that correlation, you get variances that are smaller than what they should be. And investigators like this because your effect size is the difference that you observe divided by the standard deviation. If the standard deviation becomes smaller, my effect size becomes bigger. I get significance, but it is a wrong effect size. The variance needs to be inflated properly because of that correlation. Give you an extreme example. Suppose the correlation of everybody in the village gets the exact same answer. Then the amount of information the 50 villagers in your study is giving you is equivalent to the information of one person. If everybody's exactly the same, we call that the intra-cluster correlation is equal to 1. When that happens, you lose power. If you ignore that you have that, then that's when you get into trouble. And so many people that are not statisticians don't know this. It was known since 1920s. This is something that R.A. Fisher had proposed and studied, and he knew that if I plant things in a given plot, he was working in agriculture, the yield of the plants in the same plot are correlated because they share the characteristics of the plot. The soil, the fertilizer, the water, the sunlight, etc. I need to take into account the correlation of that if I'm going to use each plant's yield. The easiest thing is I summarize it and I have only one yield per plot. But then if I get one answer per village, then I have 15 points on it. But if I want to answer each person in the village, I need to take into account that the person's data from the same village are correlated. The correlation may be very, very small. So if it's sometimes very, 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 very small, it's ignorable. If it's just only very small, it is possibly not ignorable. You can have it. It tends to be small. But when it's not clustered, but it is recurrent outcomes in individuals, now you will admit, oh, those are highly correlated. The correlation between my times to falling in a person is likely to be 0.8, 0.7, even higher. And if I ignore it and I use all of those as independent ones, which is what the Anderson-Gill model does, that's wrong. And so that's why the Anderson-Gill model was initially proposed, but now nobody's using that so much. They're using the PWP models. So the correlation is something that, yes, it's been known to be a problem. It is known not only in survival data, it's been known in all sorts of data. So even if I'm doing a study and I'm measuring, just blood pressure, not time to a blood pressure control, but I'm measuring blood pressures, the blood pressures of, or change in blood pressure in people in a village are somehow correlated. Yes, but blood pressure does depend a lot on the person. But there are other things that could be, let's say BMI. BMI in a village may be related to, this village is it's a food desert. They don't have good quality food here. They have junk food here. Most people then are on the obese side. Or another place where to get the village is situated in a way that people have to walk everywhere, and they're more fit from walking. So people are, the BMIs of the people in the same village have some degree of correlation. You look at families. Families is a cluster of friends. You have the family of the fat people, the family of the thin people, right? That kind of stuff happens. So we need to take that into consideration. Yes.
If I have done a randomization stratified by size, my intervention is 1:1. So it's an individualized patient randomized trial that just correlated because they were stratified by size and within site. Can I use any?
No. So stratification is different from clustering. Clustering is naturally occurring groups of people. Stratification is an artificial stratification that you are constructing just to balance the arms. So it's not, you don't have to do any adjustment.
So I don't need to write that while writing my main analysis in my SAP, that while doing the analysis, I will be using a cross proportion hazard model, adjusting for the stratification factors.
No, that's okay. So adjusting for the stratification factors has to be done because your variances are going to be actually lower, not higher, because you've stratified. Many people do. Oh, so those of you guys who walked in. So you are number 4 in the pink. In the white, you're number 5. In the green, you're number 6. And in the blue, you are number 7. Those are the groups that you're going to be assigned to work with an exercise. So group number 4, can you raise your hand? So she knows who is group number 4. So you are working with them. Who is group number 5? You're working with those 2 people. Group number 6, you're working with those 2 people. And group number 7, you're working with those 2. They will explain to you what you have. So now there's one group only has 8. Right, so go on. No, so when you stratify, you are doing it for the purpose of not analyzing data within a stratum. You're just doing it to balance the 2 groups. Right? When you're doing that, you are actually, stratification will reduce the overall variance. So yes, if you do the analysis, taking into account the stratification, you will have reduced variances. It's to your advantage to do it because you will get bigger effect sizes, right? But many people conservatively don't do it because they already have big, that the stratification doesn't really increase it that much. That's a stratification. Clustering is very different. Clustering is there are existing reasons, like I randomize a clinical site to get intervention A and another clinical site to get intervention B. So now the site characteristics, the populations that go to that site, and how that site behaves, even though they're following the same protocol, somehow get into making the outcomes of the people that go to that site somehow correlated a little bit. It's within site 1 and site 2. Then clustering increases. If you ignore it, you get smaller variances, so you have to increase the variance.
So in the example which I mentioned, they are stratified by site. How should I treat it? Should I treat as by adjusting it the site as a fixed effect or a random effect?
No, it's not a random. I would not. If think about what are you doing when you put in site as a fixed effect in your model? You're saying that the effect of that site on a person's individual outcome is such and such. Right? And so you think that given site has an effect. You may have 4 or 5 sites. Okay, you may want to do that. I don't usually see people interested in that question.
You estimate the average treatment effect using the hazard ratio cross proportion. My current approach is to adjust for one stratification factor, which was artificial relation and a random effect of size. And that's how the plan is. But
I don't know why you do a random effect for site. I mean, you would not expect site differences. You could do it. It doesn't hurt you to do it because we were having this argument in one of our trials. Should we expect, can we pool sites together or not? Right? And the pooling of the sites data is guaranteed because they all are supposed to follow the same protocol. So then you randomize within a site. You don't randomize sites. You randomize it within a site. So whatever site effects there are equally balanced between treatment A and treatment B. Now, if suppose that's one site recruits 90% of your patients and the other sites recruit 1%, 2%, 3%, maybe then you want to realize this, or maybe you think that there are some side effects in those small ones because they're not a good balance because they didn't have enough people. Maybe you do it differently. There is always some heterogeneity among sites, but most people don't do it. I would never do it as a fixed effects per site. If I did it, I would do it as a random. But most of the time, we don't do it. We never do it.
So if I adjust it as a random effect for trial, should I just keep it by just calling it a random effect, or can I use the term of this frailty? Because that's not actually what's happening inside. I'm just assuming some heterogeneity of patients.
The random effect, the frailty term is the random effect.
Yeah. So can I use the term?
Yeah. Yes. Yeah.
So who do we do these frailty models on? So we cluster them and then we say that that's different from covariance. So we say that these people have some difference between everybody else. And so we want to put them into a cluster. And on that, we could say we want to.
So again, clusters are naturally occurring groups of people.
Okay.
That it's the people that go to this hospital in general, people that the students that go to this school, the people that live in this neighborhood. You do not build clusters. They are the ones that are existing out there.
Are they spatial clusters? Or
Clusters of patients.
It has to be a spatial cluster. It can't be like a group of people who are older, like
No.
that way. Like
No.
these people are older, so therefore they form a cluster because
They're not a cluster. Cluster are people that share some characteristics by living together or be, mainly by living together or going to places together.
It's a spatial thing.
It's a spatial thing, yeah.
But if you take 1 year of hospital, second year of hospital, that's also a cluster, right? It's not spatial, it's like time.
You could have, cohorts that are time cohorts of spatial ones, right?
How do you decide who falls into this cluster, though? So you don't have.
The clusters are heterogeneous within themselves. Inside they should be heterogeneous. That is generally naturally occurring. They are having all variability within themselves. Whereas stratification is heterogeneous between themselves. These characteristics must be there. Now, normally, naturally forming groups will have these characteristics. A bunch of mangoes in a tree, they are all clusters. But if you are dividing the population as north, east, west, central, or their food habit, if you are dividing, then it is stratification or groups.
Yeah, very good explanation. Okay, so then this example, like the villages, we would have selected 15 villages that are similar in characteristics, but within the village, the members of the village are heterogeneous. So there's variability within, and you have very little variability or expected variability between them. And this study was looking at the time to blood pressure control in 2 months after completion of intervention. And they also had it in 3 rural regions of South India. Those would be like straight up the rural regions that they were looking. And so the outcomes of time to blood pressure control of people in a village are likely to be affected by being in the same village. And the village effect, we call it. And that village effect is to make those be correlated somehow. Here's another example. This is a traffic calming devices that were used in Ghana in the streets because cars, like everywhere, people like to go speeding. But they put particular speed humps that were different designs that they were looking at. And they call it a quasi-experimental design because they're not randomizing each car, they're randomizing roads to get this. One road gets this and another road gets there. But now they're analyzing the change in severity of road traffic injuries. This is not a time to event one, but here is it's another example of where clustering of things happen. So the injuries that happen, they wanted to see if the injuries were crashes were less severe where you had these speed humps than where you had no speed humps. And it was, you cannot randomize people to drive this way or to get injured here versus to get injured there. Right? So you randomize, you take this road sector is now the cluster. The clusters can be viewed in different ways. All right, so what are the interesting issues and questions when we have clustered design? First of all, why did we do clusters? Usually you don't do it because you want to, you do it because you need to. It's the only way to design a study. If I want to do a blood pressure intervention in a village, I cannot have the social worker go randomize individuals. So I'm going to talk to you this way and give you this group intervention. But this person, oh no, you cannot come to my group. You cannot do this. It's impractical to do it unless I do it in a village setting. I have to get consent from the village elders and then consent of individual people. There's all the selection bias because people know what I'm doing in this village. They may participate or not participate. They select them, the people select themselves to join the intervention already knowing what the intervention is going to be, or not join the intervention if they don't like it. So then have adherence of two levels of the people and also of the village. The village elder may say, go away. We don't want you doing any more of these group interventions here. Now you lose all 50 people. There's an impact on the sample size. They have to take into account the intra-class correlation coefficient. Inquiry or McMaster does it for you, but you have to take that into consideration. But so the clusters are clusters of people or intact social units that are randomized to intervention and control groups, and then the outcomes are measured on the individuals. If you measure the outcome on the group, then it's just randomized groups, and you have studied groups, but you have few groups usually. You want to get the power of more individuals. And so special cases, community randomized trials. And so the design is like this. You have possible clusters. The clusters may be clinics, may be clinicians. If you're doing counseling, like within a clinic, there was a study on pediatricians counseling parents on how to get their children vaccinated. The outcome was getting 100% vaccination, 100% of the vaccines of the child. And they were trying different ways of counseling the parents. And there were two ways. And pediatricians said, oh, yeah, I can counsel this couple with this one, and I can counsel this other couple with that. Yes, I don't care if you're the best pediatrician, you may mix the messages. You'll contaminate. So we randomized pediatrician to counseling A or to counseling B. So all the people treated by the person was getting the same counseling, and by another person was getting the same counseling. So there was no contamination. So then the cluster then becomes the clinician in that case, or the hospitals, or the schools, or villages, or some geographic location. Yes.
Tobacco cessation counseling, if we are having, so for cessation control, tobacco cessation control.
of tobacco cessation.
So if we are taking some villages, comparing that, one villages we are giving, so 5 villages we are giving some tobacco control measures or interventions, and another are leaving, taking some data.
Mhm.
So whether this cessation is control or not, we can see that, like that we can.
Yeah, because now you have a tobacco cessation intervention in that village, or everybody in that village gets that intervention. And another one, they're not getting that intervention, they're getting another one. Everybody in that other village gets the other one. But now you're analyzing individual people's tobacco consumption behavior. So those will be correlated because they live in the same village, and these are correlated because they live in the same village. So that's exactly a situation like this. Okay? Because now so the whole cluster goes to an intervention or control, but now you analyze the people within the that you're not analyzing at this level, you're analyzing at this. There's loss in power that happens here, so we must increase the sample size by what's called the design effect of the study. And design effect has to do with the average cluster size, so how big is each cluster on average, and how correlated are the observations within a cluster. It's called the intra-cluster correlation coefficient. It's not a true correlation because it is always positive between 0 and 1. And the design effect is to inflate your variances and inflate your sample size. Why? Because it's always positive. It's 1 plus, this is a positive number between 0 and 1, and M is number of people on average. So the lowest this can be is 1 person per village, but it's always greater than 1. So this is positive times positive is greater than 0. And this is now 1 plus something greater than 0 is greater than 1. So the design effect is always greater than 1. The only time it can be equal to 1 is when this part is 0. And the product of two things is 0 if either one is 0. Only way this is 0 is I take only 1 person per village, or there is no correlation among the observations, or it's very, 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 very small. So what we have to do is calculate that and find out what it is when we design our study. And then when we analyze it, we also do it. So I think McMaster has that already. Incorporates, you just tell him what is the average cluster size, and you tell him what your ICC is. Where do you get the ICC from? Published literature or a pilot study? Don't do like many people that says, look up, God tells it to them, and then they write it down, and they do the calculation then. That is not a good way to do it. Okay? God may not give you the right answer. All right, so I'm not going to go more into this because we're going to go to the how do you do the frailty model. But the main 4 characteristics that distinguish the cluster randomized is that the unit of assignment is a group of people, and then that's their own, not groups that you form, but they are rather that occur in nature. And then different groups are assigned to a condition, an intervention. And so you have a hierarchical structure of people within the cluster, and the units are members of these groups. And usually there's a limited number of groups, but many people. You want to analyze the people. There's a good didactic paper that I recommend that you read if you are planning on doing these sorts of studies. But we have correlated outcomes. So the outcome measurements from members of the same group tend to be more alike than outcomes from a different group. And so what we look at is the variation between and within group, and calculate then this thing called the intra-class or intra-cluster correlation coefficient. Intra-class is a more general term, but intra-cluster is used. And it's the extent of between group variation. And it's a proportion that looks like that. So at the analysis stage, the outcomes at the cluster level, we have few units, we have reduced power. And so if we analyze at the cluster level, we must usually use non-parametric methods. So three people walked in. You are number 8. You are number 1. You are number 2. That's for your homework. You are assigned to group 8. You're assigned to group 1. You're assigned to group 2. So group 8, raise your hand so you know you're working with these people. Group 1, raise your hand so he knows who you're working with. Group 1?
Yes, sir.
Then group 2, raise your hands. So he sees who she's working. You work with those people. All right. Sorry to embarrass you, but to assign you to your exercise group. We usually don't want to do analysis at the cluster level. We want to do analysis at the participant level because we have many more participants. But that correlation among them reduces the amount of information that they're given. If they are uncorrelated, they're independent, and I have 50 people per cluster, then the information that I'm getting is for 50 people. But if they're perfectly correlated, then I'm getting information of 1 person. We usually are never 0 and never 1. We're somewhere in between. And you like to be on the smaller side so that you get more information. The cluster level and participant level beneficial effects impact the analysis at the end of the study as well as the interim analysis. The standard approaches do no longer apply. And depending on the type of outcome, there is adjustments. Now, in the slides, I have it for binary outcomes and continuous outcomes. But for this course, it's time to event outcomes. So I'll skip the other 2. So we must account for the design effect and even in the crude analysis. So for binary outcomes, we're doing a chi-squared statistic. There's adjustments for the chi-squared. You do continuous outcomes, you're doing a t-test. There's adjustments for the variance on the t-test. What is the adjustment for time to event? So when we're doing time to event analysis, we have different analytic tools that we can use for it. And the one that, if you did the Cox model, or the log rank, you need to be adjusted. How do we adjust it? We call those frailty models. That's the adjustment that the frailty models are basically to deal with correlated data that we have. Okay? There's other ways of doing it, and that's called you can do it with the generalized estimating equations and marginal models, but it's not that commonly done. Frailty models are introducing a frailty component to the Cox model. The same Cox model that we saw yesterday. How does this work? So, a frailty model is a model for the hazards in which a multiplicative random effect is added or included in the model. This is what is called the frailty. It is a random effect that's added multiplicative. How is this done? This is relatively simple. You have the Cox proportional hazards model. If you remember from yesterday, you're modeling the hazard function over time, how it's affected by covariance. What Cox proposed that got him knighted was to decompose the hazard of a person into a part that includes time but no covariance, and a part that includes the covariance and no time. He used the parametric exponential distribution to have us include the covariance that way, but he said this non-parametric, whatever it turns out to be, that's what it is. Because what they were interested in was in the hazard rate ratios of the different covariates, specifically the intervention effect, one of those covariates. But now what I'm doing is I'm saying that I'm going to give, if I have 10 clusters or 15 villages, Each village, 1, 2, 3, up to 15, has its own underlying hazard. So the I should have put I equals 1 to however many clusters I have. If I'm doing repeated measures in a person and I have 100 people, now I'm given a subject-specific underlying hazard or frailty. So I will have 100 of them. I will go from 1 to 100. So everybody gets a cluster-specific or person-specific underlying hazard. Okay. Now, what is this one? Well, this can be, again, unspecified, but in some textbooks, they can just leave it like this. Some textbooks like to say, well, this is whatever the hazard is of a given person, it's a multiplicative on the underlying baseline hazard that everybody has. We have the shared baseline hazard, and we multiply it by some zi, and that becomes the underlying hazard for the IF person or IF cluster. And so they call it the ZI, not the lambda 0I, but the ZI is called the frailty of the IF cluster. Questions on that? Now, why is this done? This is done to account for the correlation. It's not something that I am interested in reporting. I'm not going to say this is the effect in village 1. This is the effect of my intervention in village 2. This is the effect of my intervention in village 3. If I did that, then first of all, it sounds kind of silly to say my intervention works differently in different villages, especially if my intervention is a drug. I don't think any pharmaceutical company would like to say my drug works better if it's given in Ames than if it's given at CMC, than if it's given in this other hospital. No, I want my drug to work everywhere. So you're not interested in what is the effect in each clinic, in each village, or if it's a repeated measures in a person, in each person. Oh, in Mr. Mohan, the effect is this. In Mr. Balasubramanian, the effect is this. No, the effect of my drug is the effect of my drug. So nobody cares about this. That's why it's a random effect. It's not a fixed effect. We don't care. We just want to deal with that correlation because we have to deal with that correlation. Now, how do we interpret this another way is we look at that frailty as a random intercept in the Cox proportional hazards model. So this is what that formula that we had in the previous one, right? At the bottom, we had that the frailty term is this, Zi this. So what if I plug this into the Cox model? So now I'm taking this and plugging it there. What I'm saying is that the Cox model now becomes this. I have the original Cox model, but now I have the frailty term here. Because I've individual one have decomposed into the frailty and the overall shared underlying hazard. Now I'm going now to math, and I'm taking what? I'm taking this. If I think of Zi as e to the beta Zi, so I now take this is I put it in this function. Intercept beta 0I in the model, in the linear model. So the log of Z of the frailty model is the random intercept for frailty in the model. This is just mathematics. This is not statistics. This is just taking that and plugging it in here. Does everybody see this? Questions on this? This is coming from the fact that the Cox model is lambda 0t e to the beta x, right? But beta x is beta 1 x1 plus beta 2 x2. And if I put beta k covariance or xk covariance, that's what that is over there. And what I'm saying is that I give this a frailty. The frailty, I can have it as 0i_t or zi_0t, factor it out either way to do that. So now what I'm doing is I'm taking this and trying to put it up here. But to put it up here, I can say that take zi, and make it e to the beta 0i. Just why? So that beta 0i is nothing but the natural log of zi. So if I have this, now what do I have? I have that this whole thing is lambda naught t e to the beta 1 x1 plus beta k xk. And now that zi is e to the beta 0i. So this is e to the beta 0i. This is why I say this becomes your math here becomes that this can be lambda 0 e to the beta 0i plus beta 1 x1 plus beta k xk. And then this I will consider as a random. When we fit the model, what do? We'll have this is lambda t x. When we fit the model, we take the natural log here, we'll linearize it, natural log here, so natural log of this, plus natural log of this, the e goes away, and now this is, you can think of this as the underlying hazard beta 0, and this is beta 0i, random effect for the ith cluster. And it's an intercept there, the random intercept effect for the ith cluster. That's just the other way of thinking about the frailty term. But the frailty term is what? It's at beta 0i is the natural log of the frailty term. And whether you like to talk in terms of natural logs or whatever, that's what you do. Now the frailty terms are just there in the model to account for the correlation. You don't report them. In fact, most softwares don't give it to you. Because first of all, you'll have, if you're doing 100 people and you have repeated measures in a person, you're going to have 100 parameters there. You don't care. You're not going to report them. So they just save time by not reporting it to you because they know they're not of interest. You only do them to account for the correlation. Questions on that?
So the right stands for each cluster of factors. So that. So if I have 4 clusters, so Z starts from 0 to 1 to 4.
Yeah. Now comes another question. So when you're designing your study, if you're going to fit random effects to the model, the preference is that you have more than just 4 clusters. You want to have many clusters rather than fewer clusters. So you would want to have, let's say you have 1,000 people in your study. Is it better from a statistical standpoint to have 100 clusters of 10 people each as opposed to 10 clusters of 100 people? You get more power by having more clusters than of small size than you do a few clusters that are big. It all depends on how much correlation there is within them. True. But if you had 100 clusters, 1,000 clusters of size 1, then that's the most efficient, right? But yes, you cannot call it cluster. So where is the sweet spot here? It depends not only on statistics, it depends on logistics, and it depends on cost. So if you're doing 10 clinics of 100 each, you have to only find 10 clinics. You only have to train 10 people. And hopefully you can find them in your city. But if you have to get 100 clinics of 10 each, You have to drive all over the place, you're all over the district. It's expensive. You have to train 100 people, 100 sites, and you have to then, of course, monitor that they're doing it correctly and all sorts of things. You have more sites to monitor, and they're only contributing a few each. So statistical considerations are very different from logistic considerations. And in every study, when you're designing it, you're doing a balancing act of what is optimal for your situation. So interpreting the frailty term is there, even though we don't present it, whatever. The frailty term, what does it stand for? It stands for, if I'm doing a cluster trial, is that it's basically telling you that each cluster has their own hazard rate. That underlying lambda 0t, you have it their own one. And the clusters with the same intervention have the same effect. And the effect of covariates in the model is the same for all clusters, because that's the beta x is the same for all clusters. If you're doing frailty models for repeated outcomes in a person, each person has their own hazard rate. We call it subject-specific hazard rate ratio, or hazard rate in this case. And the effect of covariates in the model is the same for all of the occurrences within a person. So interpretations are different depending on which way you got the correlation in your data. But this is the bottom line, I guess, for frailty models is that you need to know if your data are correlated and why that correlation is happening. If you can assume that all the observations in your data sets, suppose like in our data set, we have 2,358, they're individual people, and individual people were randomized and not clinics were randomized, then we can assume that they're independent. And we don't have to worry about frailty models. We only worry about frailty models when we have designed the study to have correlated data. And the only reason we do design a study that ends up with correlated data is because we have to. It's the only way to do that study. There is no way I can counsel people individually. There's no way that I can have multiple falls in a person being independent. They are what they are. They are within a person. Or if I'm studying multiple people within a family, or I'm taking a cluster and doing a sample design in an observational study I do a multi-stage design where I take some districts and then I randomly select neighborhoods and then I go to villages or streets there, and then I take households, and then I take everybody in the household, or I take all the elderly people in the household. Now I have a clustering of the elderly within a household, for example, and the elderly from a village or the neighborhood. So we have multi-level analysis. That goes even further from the frailty term. You can have complex frailty term. This is a very simple frailty term with only one random intercept. But if you had done your study where you had taken, and you want to do it by clinic, but suppose the clinics were clinics in a given community, and you took multiple communities. Well, maybe something about the community, if it's a poor community or rich community, has an effect. Now you have a frailty term for community, and now you have another frailty term for clinics within community, for example. So you could have it as complex as you've designed your study. What I'm saying is that this is a way to deal with correlated data. Nothing more than that. Yes.
I really like over your cardiovascular study for the made the composite outcomes.
Mm.
You could do it as giving treatment, like a patient in the heart area, and then that person, right now you're thinking first outcome. So theoretically, that person now is at a higher risk for death. Like you had an MI, now you're during the course, you had an MI. That increases your outcome of possibility of having a death, right?
Yeah, right. So okay. So now you're saying you're taking a person and you're looking at the time to outcomes that are part of recurrent outcomes or repeated time to events in a given person. So you have time to the first of either um, MI or stroke or heart failure hospitalization or CVD death. Let's say you get the time to the MI. Now the person, treated or not treated, whatever, you make the assumption the person is still at risk for any of these things again, and that their risk is the same as they were at baseline. This is not a great assumption, but you make that assumption because they have been treated and maybe they are better or they are frail or something.
Isn't that where that each person has that enough changes?
No, you don't. This is the problem. It does change, but we don't have yet the way of adjusting. We don't have the tools, but now you have the next one, and the next one may be the time to the next event, and that one happens to be the second event. And maybe it took a long time, or maybe it took a short time because you already had one amount. Well, now you have that other time. Okay, now the person, let's say, is not dead, and the person now is followed and continues being followed. Now they get a stroke. So now you have 3 times 2 occurrences of one person. How you analyze those 3? First of all, you have to make all these assumptions that those are they independent? No, they're not. Are they the person the same risk? No, they're not. But we'll assume that they're the same risk. Now I have 3 time to event observations in my data set. But they're from the same person. They're not 3 independent ones. Then the cluster of a person needs to be taken, the correlation of the person needs to be taken. That's when you put in the frailty term of the person. For those 3 observations, they come from that same person.
Like an article that has this population issue that was like sort of
So this article here gives a nice little tutorial on it. It is came out in 2020, is that it? Yeah. So it's relatively recent. The Statistical Methods in Medical Research Journal is review articles. So this is a review article, and it does go into that. The example that they give is not that great, but that's, yeah.
In this context, if you had a second person who also had the MIs, would they also fall in that same cluster?
In their own cluster.
You can't make 2 people in one cluster because they have the
You can't construct clusters. You can't, clusters are naturally occurring groupings of things. You cannot artificially create a cluster. But so yes, what I'm saying is this: if we go here, let's take these 2 people. So these 2 people are, so this is person A. And person A comes here, and here they have an MI, and they are not dead. And then they get the second MI, and then they get a stroke, and they continue being followed. And now the study ends, and the person is censored at that time point. Now you have person B, and person B comes in and gets a stroke here, and then has cardiovascular death. And that's one of your outputs. We're going to complicate it in a second. But let's say it was this. So what we have is, this is one time A1, because it's person A for the first event. This is time A2, and this is time A3, This is time A4. This is, for this one, it's time B1. This is time B2. Okay. Now, in your data set, what are you going to have? You have observations. You have observations 0, 0, 0, 1, up to I don't know how many observations, 2,358. You will have an ID of the person. This is person A, and observation 002, 003, 004 are all of A. Observation 005, 006 are all of B. Then you have what? Time. And you could have time to, we'll call this event. This is the assumption that people are making. This is cardiovascular event, and MI is the same as stroke, is the same as CVD death. So here you have event, here you have event, here you have censored, right? Here you have event, and here you have event. So now you have the time and you have the event one. So this is the time here is TA1, TA2, TA3, TA4, and the event is 1, 1, 1, 0, because they were censored. Then you have here, this one is TB1, TB2, the head event. Yeah. The thing is that if you put it in your software, I don't know, 12,000, whatever, and you dump it like that, the software is stupid. Software doesn't know that, unless you tell it, that observations 1, 2, 3, and 4 are correlated. You have to tell it that it's correlated. And there's the commands for telling it this is the cluster. And then 5 and 6 are correlated. Otherwise, it'll assume they're independent when they're not. Okay? Yes.
How does the correlation or this Frailty within a system affect the final hazard? There is a lot of skepticism within the cluster. Does that cause your final hazard to be accurate, or how is that reported?
No. So the frailty term, what it does is recognizes that there is a village effect in the correlation, not on the hazard. The hazard is whatever the hazard is, and it is what how good your intervention is in reducing the outcome that is the bad outcome. So it doesn't. The frailty term doesn't have anything to do with the hazard. It has to do with the correlation among the observations.
So when I look at the paper which reports in a study, how do I
Report both, meaning?
and it gives you the correlation, the Frailty term, and it gives you
Give you the frailty term?
I mean, it tells you the correlation within a cluster. That is
So they give you the intra-cluster correlation coefficient. Yeah.
or tell you how much is the effect of the cluster on the what is the I mean, like what's
They
the-
cannot give you the effect of the cluster. It's a random effect. You do not get the estimate. But they cannot. They must have put it as a fixed effect in the model. If they would have said, we put in a dummy variable for people that are members of this cluster, and the coefficient attached to this specific village was this. So therefore, the effect of that village was this. That's the only way. If they do it as a frailty term, it's a random effect. They don't know what it is. They don't report it. They would not have reported. The only thing they would be able to report is say the amount of correlation in their data was this within villages. Was this.
I think
But they give the design effect. I mean, what they could do is, what he's saying is that they may report the design effect, which is 1 plus m minus 1 times the ICC, right? So they calculate this, and they say the amount of correlation that there is within a cluster is 0.0023, and we had on average about 150 people per cluster. So this is 149 times 0.0023 plus 1, and it is 1.03 or something like that. So that's the design effect. That's what they would give. But the only utility of doing that is to help other future researchers when they're designing their study. But it doesn't mean anything about the hazard or anything about the goodness of the intervention or anything like that. It's just
not on the hazard, that is what service also mentioned. Basically, when you have to say it's significant. See, when you don't adjust for the clustering, you usually say that there is a not significant result. But that's because you have not taken into account. See, when you talk about a cluster, there are two variances that you're dealing with. One is between the two individuals and also some variability within the cluster, right? So even if I have my own readings done measured 3 times, there is a variability within myself itself between the readings. So there are two variabilities that you have to account for. But when you have independent observations, it's just only one, because I'm giving only one, the another person is giving another reading, so it's only one variability that you're talking about. But here the variance is more. So what happens is finally your end result, you might say that there is a significant, I mean, do I say type 1 error? Okay. So what happens is, if you don't account for the clustering, your final end result, you will say that if there is a significant finding, but it may not be true, because your denominator, where you usually when you calculate the p-value, is difference divided by standard error, right? So your standard error will be much lower if you don't account it for your clustering.
so just to do that visually, when you're doing your hazard rate ratio will be based on the effect of the intervention in one arm versus the effect of the intervention in the other. Let's say it turns out to be 1.63, making up a number. You can also give the confidence interval for that. How do you construct confidence intervals? You have to know the variability of the statistic. So the variance of that HR is different if you account for the correlation or if you don't account for the correlation. So you will say 1.63, and if I don't account for the correlation, so I ignore the correlation, let's say ignore, I may get that this 95% confidence interval goes from 1.08 to 2.33, given my sample size. But if I properly account for the correlation, then the variances are inflated. And the variance getting inflated may make the 95% confidence interval what? Wider. So it may go from 0.97 to 2.43 or 6. Now, because you all believe in the magic of the 0.05 and significance, and you love p-values, you are going to commit suicide because you did not get an effective intervention. That's the only reason.
For the variance, accounting for the effect of the cluster makes your
Yep. Makes it
confidence
wider.
interval wider.
okay.
So that design effect is called by people that work in sampling the variance inflation factor, VIF. People in epidemiology call it design effect. It's exactly the same thing. What it does is it inflates your variances because you have to inflate. It's not because you want to inflate. You have to because you've done it.
Okay. So if I was reading an article, I would look at the statistical method to see whether they have accounted for it. That's what you need to do.
Exactly.
They're not going to give you a quotation, they're not going to give you a variance. They will just say, we have accounted for clustering using whatever.
Yeah.
And then gives you a hazard. So you have to interpret the constant interval based on whether they have had whole new.
Exactly. And the thing that used to happen.
If they haven't, it may be that it's not relevant even though they said it has. So then you assume that there could be it's like a exaggerated.
No, so you do critical appraisal, right? So when you're looking at the article, you say, I don't trust you because they didn't mention this. They should have because their design led to correlated data and they didn't do it. So I don't trust this paper. And after it's published, you can write to the editor. It used to be that, I said, we knew about this since the 1920s. The calculation for not just the binary and continuous or time to event was cumbersome. And there was no software for this. People would not do it by hand. So they sort of ignored it nicely. And in the 1980s and 90s, most papers you still see didn't account for it. But now the software is there. There's no excuse to not do it. And some people say, oh, no, I did not know. And now their editors and statistical reviewers are demanding, you should, I don't care if you don't know, it is there and it's available, do it. That's the proper thing to do. All right, time for a break. Enough cluster. Let's cluster upstairs so we don't get frail. Some people miss. This is actually the next topic is when we're having lots to follow up that's informative. Maybe the people that are dropping out are those that. Yeah, will improve their outcome. The outcome being satisfaction with the course. All right, so now we're moving on to the second advanced survival analysis topic of joint models. And as I've been saying, this is a very active area of methodologic research in statistics at the moment. There are methods to deal with things. They're not well known, but you're slowly starting to see it being reported. And I would say maybe in the last 5 to 10 years, things have been occurring with it. And now we also have software to be able to do these models. And what are joint models is when we have an interest in a time to event variable, but at the same time, we're looking at repeated measures of some biomarker or some variable that is of interest that is somehow also related to that event. And I'll give some examples of this to try to motivate why we have these complications. Complications are ones that are not dreamt up by statisticians. These are complications that come from ideas that investigators dream up because they are of clinical interest to their research. But then there are issues in how to handle things statistically. So then statistical methodology needs to keep up with this ideas. So let's look at what happens in longitudinal studies. We have prospective medical studies, are recording data, right? You're interested in time to some event, but you also have some variables that we considered as not changing. For example, the sex of the person. For example, maybe their education, their socioeconomic level, their past history of such and such, their genetics, etc. These are things that we consider as fixed covariates that may affect your time to event variable, when it occurs, if it occurs or not, but they're fixed covariates. But we also have longitudinal repeated measurements. So we can measure some things along the time that are changing. We could have, for example, your blood pressure may be changing. Your EGFR is changing. We may have other things that are changing. Give the example of in HIV, one of the things that's changing in people that have HIV is their CD4 count. And so let's say we take this study where the CD4 cell counts are collected at entry, and it's collected at month 2, and month 6, and month 12, and month 18. But we're also interested in time to death. So our outcome of interest is a time to event. It is a what many people with HIV are interested in. As I mentioned, I think as an example yesterday, when HIV sort of appeared in the scene in the early 1980s, 81, 82, it was a death sentence because there was nothing that we knew about this disease and how to prevent people from progressing from HIV to actually AIDS, to then getting opportunistic infections and then dying. And so the one of the things that was known to be related to death was the CD4 counts. And so one thing that one would measure normally is CD4 counts. Well, how frequently do you measure the CD4 counts? If the person is hospitalized, maybe you could measure it every hour, every day, once a week. It's costly to do it. You don't measure it. When you're doing a regular study, you don't collect it every day. You can't, if you're doing a blood pressure study, you could ask somebody, or now they have devices that people wear. You could measure the blood pressure and report it and collect it every second. You can look at other things like heart rate, etc., every second. But most things that are repeated measures of a covariate are collected at a few time points. And so people with HIV are dying in a pretty steep survival here. But you see that their CD4 cell counts, they're going up and down, they're all over the place. And so you're interested in studying both processes. So this is what joint model is. It is when you're interested in two processes. You're interested in the process of death, in this case, but you're also interested in the process of CD4 counts. And they're related. If you die, can't get any more CD4 counts. And the CD4 count being low is what we call a good surrogate predictor of the outcome of death. So now you're interested in two processes. how do we go about dealing with this? So now this is what happens. Investigators in HIV come to the statistician. I'm interested in these two processes. What do you do? Oh no. We had to devise ways to deal with this. So the way to think about this is thanks to a colleague of ours at PHRI, Chintani. She was reviewing the literature, and the joint model literature thinks of these things, the covariates that are changing over time, not the fixed baseline ones, but the things that are changing over time can be thought of as two separate groups of covariates. We have the exogenous ones and the endogenous ones. By definition, exogenous ones are external to the person. The other ones are internal to the person. The exogenous ones would be things, for example, like the air pollution, season of the year. They may influence the rate of failure over time. So they do have an effect. But the path up to time t, so how long is time to death, for example, is not affected by the occurrence of, the measurement of the air pollution or season or whatever is not related to the occurrence of failure. It's not affected by failure, or it's just whatever's happening outside that may impact failure. That's very different from the endogenous ones, where these are measurements that are taken on the subject under study. They can be your biomarker, or clinical parameter like CD4 count, that is related to your risk of death, for example. They require the survival of the subject even to be there, right? Because the person is dead, you can't get a CD4 count. They are typically measured with error. That's because everything has random variation. But their complete path, so having people with full CD4 counts up to any time t is usually not fully observed, right? Nowadays, we may do it for some things, but not. The clinical parameters are known at some patient visits only, and not between these visit times. So we have like CD4 was at 2, 4, 8, and 12 months, and not every month. So one way to deal with this is, first of all, the exogenous variables that are time dependent can be dealt with, the exogenous ones, so the ones that are outside, time dependent. You can deal with them in the extended Cox model, where you include now time dependent covariates in the model. So for example, this is the Cox model, but we have some of the covariates now vary with time. Okay? And so the Cox model has, again, the usual underlying hazard, and now you have this, but now you include how hazard is impacted by a time-dependent covariate that's a function of time here. So the beta are for time fixed, and the gamma are for time variant covariates. So you can extend that Cox model for time-dependent covariates. And this has been done. It's fairly standard, and it uses a counting process formulation. And so this is an example of how you would have your data set up, where you have this one person has no change in their covariate, but let's say this CRP is changing over time, and this person has it 113 at one time point and 144 at other time. So the things that are fixed for the person is which group they were assigned to, their age is whatever it was, and the first period between 0 and 110, their covariate value was 113. The next period from 110 to 121, the covariate value is 144. This is what the data set would have to be set up in this way with a start and a stop for the periods when the things are changing. Yes.
In some of these, like if you're checking your CRP at a longer interval, so if you're checking it after 2 years, the age doesn't stay the same anymore.
Right. So
So
then
does this change according to that as well? Or is it only if you're looking at something within a time frame where this is a fixed value?
no, I mean you could change the age, but usually the way we treat age is to say that people age at the same way. So we just put age at baseline. So that age at baseline is never changing.
But when you're looking at a survival analysis over 5 to 10 years, how can you say that the age at baseline is what is the most important factor?
Good point. People should do that and change it and say the age, you can do age as a time-dependent covariate and just do it that. But that would be a nice way of treating this. It leads to more complication in doing it. Most people are lazy and don't do it. But you are correct. If you think that your current age is important, then yes, one would want to do the age. But usually, unless we have time-dependent covariates, if we don't have time-dependent covariates, we treat age as baseline in the models. Right? If we're going to do time-dependent covariates, then age should be one of those time-dependent covariates. I agree with you. Yeah.
If I age by 5 years in the 5-year follow-up study, he also changes his age by 5 years. My reading, unless your data deals with a lot of mortality, censoring, and so on, and my reading is that it will not change very much. We can look at it whenever you have a data. You can try that one. Both options.
Yeah.
And study that. My reading is that it will not change very much.
The start and stop is a unit of time.
So the start and stop is a unit of time that when things change of your time-dependent covariate. So for example, you take subject 4, their CRP was measured at 18 days or at baseline, and from 0 to 18 it was 72. They were measured again at age 18 days, time 18 days for the next year, and it was 110 at day 18. At the end of the year, they measured it again, and it was 90. And so you see that each person has their covariate changing over time, and then the start and stop is when it is constant within that there, but it changes. So it's a little tricky in setting up the data set for this. And this is the way to handle time-dependent exogenous variables. It's just to extend the Cox model in this slightly more complex way.
And recurrent events model, because recurrent events for a single person over the period of time.
So now you're combining two things, right? So you can have recurrent event analysis where you have in the frailty, you can have time-dependent covariates, and then you would do something similar to this as well. So now you get in two problems together, right? It's possible to do that. Now, the extended Cox model assumes that time-dependent covariates are predictable processes, are measured without error, have their complete path fully specified, and the change value at the follow-up visits and remain constant in the time between visits. And that's true for the exogenous ones. But it's not reasonable to assume that the time-dependent covariates remain constant between visits, especially if the visits are several months apart. Things change.
line have their complete path to be specified? What is that?
The complete path is that particular variable is known its values at all time points. So the CRP, the path of the CRP over time for a given person is known. It's not known completely, but we are assuming it's known because we measure it only at specific time points. We don't know what it is happening in between for this person. We don't know what their CRP is between 0 and 110. We just know that we only measured it at 110 and at 121. And at 0 and at 110. At 0 it was 113, at 110 it was 144. But we don't know what it was at 50. We don't know what it was at 75. And this is in between. But also, as you follow people up, let's say you're measuring not CRP, you're measuring the EGFR, or you're measuring their CD4 count. As they're getting worse and worse, their risk of death is increasing at the same time. And so now you have that you may not have the CD4 count if they die. So you have the death, which is a process you're interested in, becomes a competing risk for the process of CD4 count. So you have that the CD4 counts, their decline and their path is informing you of the risk of the death, and the death is also affecting the observation of the CD4 count. So those two things, those are two processes that you're interested in. They're some way competing with each other. They're highly related to each other. That's the complication that these joint models try to deal with. So the data that you have then is you have repeated measurements over time. You have these exogenous risk factors that change over time, like air pollution, and I also added here access to healthcare. You have endogenous risk factors that are these clinical biomarkers on that person. Their CD4 counts in studies of cardiovascular disease, we're more and more looking at the role of cognition and the occurrence of death and cardiovascular related death. Also kidney function parameters, right? Or lipids as endogenous risk factors. Then you have clinical outcomes like the diabetes, hypertension, etc., that could be considered as one like hypertension. That is related to CVD death. It's a surrogate marker, just like the lipids may be, or cognition may be, or your BMI could be. It's related to that. So they're clinical things, and then you have events that happen to you along the way. You may be interested in all of these processes, right? You usually are. And that's super complicated. What I'm going to show is a complicated model for dealing with one of those things, like CD4 and a terminal outcome. But if you have multiple paths of multiple endogenous risk factors and multiple clinical outcomes that you want to study, nobody has done this yet. You want to do a PhD in statistics? Welcome. We need people to figure this out. People have not figured this out yet. It would be ideal if we can figure all of these things out.
Maximum 2 available?
Maximum?
2 is available at least. It is
I think
modeling.
joint modeling, I think it's only with one of these processes as well as with the terminal process. One of the biomarkers and one of them. In theory, you could actually think of all of these things being related, but I don't think anyone has been able to figure out how to compute that. Because what would you be interested in? You're interested then, oh, what is the path of CD4 count over time? Okay. What is the path of, and I don't have opportunistic infections as well as with CD4 counts over time, but now I have terminal death. And I could have the competing risk of death from, interested death from HIV, but I could also have death from something else as competing with death from HIV. So now you have competing risks, you have multiple recurrent events. Now, suppose that's with HIV. Suppose I'm doing heart disease. Now I'm interested in your lipids as they change over time. I'm interested in your, what is it, troponin or BNP, pro-BNP, etc., changing over time. But now you have heart attacks and you're having this, so you have recurrent events that are occurring. And I'm interested in modeling those two. And I'm looking at CVD deaths, but I have all other non-CVD deaths as competing. Yeah, we can conceptualize all these complex problems, but we have to figure out how to do the analysis. No one has figured that out yet. Maybe somebody's doing this as a PhD thesis somewhere, and they'll get an R package out for it, maybe, maybe not. But anyway.
How do you think about this problem, the approach of multi-state model?
That's why I think multi-state models is a way of looking at this nicely, because you have,
They open the path.
yeah, but see, you can, that's a good point, because you can be healthy as a state, baseline state. You can have bad endogenous risk factors, like your EGFR is poor, or your lipids are too high, or your CD4 is too this, but you haven't had any outcomes. Or you could then have an outcome that's bad, and then eventually you die. So you can have four. But it's an oversimplification of the processes, because all of these processes are related to each other. So I could jump from one to the other and then go back to being treated and having just my elevated or low CD4 count. And, you know, so things go back and forth. It's not a clear ordinal path from this to death. So the states are hard to define. And I think, but it is a logical thing to be thinking about.
It may be a difficult thing to estimate the treatment effect in case of RCT with multi-state model. If we are thinking about this thing.
Because yeah, so the treatment effect in a multi-state model that we talked about yesterday would be the treatment effect on different parameters of the multi-state model. So one parameter would be the transition probability from state A to state B, and the effect of the intervention on that transition, or the effect of the intervention on transition from B to C, or the effect of the intervention on the amount of time I remain in state A, for example. So then you have now different parameters that you're interested in. So I haven't seen multi-state models used in randomized controlled trials, because it's not clear now which is the outcome on which to design the study, right? And so if you choose one, now you can, yeah, model the whole thing as multi-state, but now you focus on only one parameter to that, because the design of clinical trials is to study one question, not multiplicity of questions. And if we have multiplicity of questions, yes, we can do that. But how do we deal with multiple testing of correlated transition probabilities and permanency probabilities? Those are all very interesting questions. That's the second PhD thesis in statistics that we have come out from this workshop. So all of you will be working on some of these things. Yes.
Some new salivary biomarkers have been identified for oral cancer. So for that, some articles they have given sensitivity. So here, this is the giant models. What is the difference between?
Totally different. So there, what you're saying is that people have identified new biomarkers.
New salivary biomarkers.
Yeah. So one thing is to identify a biomarker, but then the other one is to see the evolution of that biomarker over time when there is interest in studying another process that is competing with you observing that biomarker over time. That's what joint model is. So I'm interested in CD4 count over time. That's a process that I'm interested in knowing. But I'm also interested in how is the time to death. But I'm also realizing that the time to death process is affecting my ability to study the process of CD4. So if I have a new biomarker being identified and I'm interested in a new biomarker, yeah, then I end up with also interested in the process of that biomarker over time. And if it's related to death, because it's a biomarker for death, then I would do another joint model. So yes, so now you could have the joint model with two processes of biomarkers and one of death. And I'm saying these things are very interesting, but the software and the, probably the methodology, I haven't seen the methodology developed. So then there is definitely no software. But yes, if you're interested in two processes of biomarkers, that is of interest to you, it's of interest to you. Nothing wrong with it. All right, so yeah.
Can you have covariance in a multi-state model in itself?
Covariance
So,
between
like,
what and what?
If you're looking at, so it's like cancer treatment, you take the treatment, then you go into relapse. I mean, like you go into remission and then later on you go into relapse.
Okay.
Then you look at the baseline amount of whatever the malignant cells or parameter of the malignancy. And you're monitoring the malignancy parameters over time, which is basically what they do in hematology. So as they monitor the parameters, when they go up, it kind of predicts that you're going to go into relapse.
Mhm.
So how would that fit into, would that be a multi-state model or would that be like a joint model?
It could be a joint model because you're now having the process of the, what was it, the cells that you're looking at over time. That's the process, measuring the amount of these particular cells. And now you're looking at that path of those cells over time. They are highly related to the terminal event of relapse. Let's call it terminal, or it could be death. You put together a composite of relapse or death. And that's the second process. The time to relapse is what you're interested in. And time to relapse depends, as you say, on these cells. And the observing of those cells are going to be stopped when you are dead. So it's exactly a situation of joint model. Except that, how you quantify the presence or absence of certain cells, that's the metric that you have, right?
That's where relapse is the endpoint, or death is the endpoint.
Yeah.
But along the way, you can have a clinical relapse, you can have like a.
Now you're giving other outcomes. That's different. So now you're giving in not a terminal outcome, but you could even consider your clinical relapse as your outcome. Just like we are doing in this exercise, you can choose what you think is your important outcome to study. Maybe my important outcome to study is stroke. That's what we have, one example, right? So that's what I'm interested in. That's what my outcome is. And now I can have competing risk for it, or I cannot. What I'm saying is that once you've chosen your clinical time to event outcome, could be death, it could be clinical relapse, or it could be either one of those as a composite. That's one process, time to that outcome. And now I have another measurement. And so these cells, we will say that we stop measuring them once the person is in clinical relapse. So then, yeah, it is a joint model. You don't have to, so clinical relapse becomes your terminal thing because you don't, not terminal for the patient, but it's terminal for your information. So the question is, you're interested in two processes. One can focus on one or focus on the other. So if you're interested in modeling the repeated measurements over time, jointly considering the time to event as a competing outcome is one way of thinking about it. Or you're interested in modeling the time to event outcome when the hazard depends on the repeated measurements. So your focus may be more on one than on the other, not reporting both. But joint model will deal with this situation. So what is it? So the primary interest in joint modeling is the association between those endogenous time-dependent covariates and survival. So those biomarkers that are changing over time. And so what we do here is we're trying to jointly do both models. The survival model with a suitable model for the repeated measurements of the endogenous covariates. So statisticians are not very clever with coming up with names. So the one is you're modeling the survival, but it's modeling the survival in a submodel. If you're doing the longitudinal one, I'll call it a submodel. So we have a survival submodel and a longitudinal submodel. Those of you that are not interested in the formulas, we can ignore the next two slides. But the survival submodel then is looking at modeling. This thing turned out so great here. The time to event outcome, and you have the true event time and the observed event time. And so you have M sub IT is the true and unobserved value at time point t, and you have the observed value at time point t. And so you have this whole covariate history that is being put into this model. And so you're modeling the survival, taking into account the whole covariate history. And I guess these are some weights that you put into this model. But it's the same thing. So you want to say, what is the probability of surviving? What is the true event time, considering the whole covariate history? And we end up with something that is very similar to, it's again an exponential one. And this is the survival. You can think about it with this model. Don't worry about the formula. Then we do the longitudinal submodel of this MIT, which is the true value of the underlying longitudinal covariate at time point t, which we need to estimate and successfully reconstruct the complete longitudinal history so that we can then put it, we get the complete longitudinal history of the covariate to then plug it in over here. And so, whoops, turn it off. So what we end up doing is postulating a suitable mixed effects model to describe the subject-specific time evolutions. So the standard Cox proportional hazards model usually have the underlying hazard unspecified, but the joint modeling framework explicitly defines that underlying hazard to avoid underestimation of the standard error. And so they will use things like the Weibull or log normal or gamma, and they do more flexible models than the linear model for the covariance. And now we're going to have an illustration that Dr. Vishali is going to do with HIV and CD4 counts. But let me just sort of introduce the problem. So, and it's sort of what we've been talking about before. So a person with HIV, their true CD4 will decline over time. The clinician and the patient would like to understand the factors associated with the decline, non-decline, or even increase over time in CD4. So we're interested in the trajectory of the CD4 count. This is what we call the path. The HIV patient may get some opportunistic infection and may die from the infection or die from some unrelated cause. So we have a competing time to event outcome on observing the CD4 count. So we model the time to event outcome and consider CD4 as a time-dependent covariate, but the CD4 is not measured at every time point. And so we end up having to do a joint model because of that, the problem with not observing the CD4 at all time points. Another example is the one that we are facing in one of our studies at the Population Health Research Institute, and that is cardiovascular disease and cognition. And cognition, how it declines over time, has been said to be related to getting cardiovascular disease and dying from cardiovascular disease. So you have elderly CVD patients, true cognition declines over time, and the clinician and patient would like to understand the factors associated with the decline, non-decline, or even increase in cognition. So we're interested in the, again, trajectory of cognition over time. But the CVD patient may get a stroke or heart attack or heart failure, and then may die from it or die from some unrelated cause. So that's a competing time to event outcome that is competing with the cognition path. We want model the time to event outcome like death and consider cognition as a time dependent endogenous covariate, which is not measured at every time point.
When you mean not measured at every time point, are the time points already fixed or determined beforehand?
Usually in a study, they're fixed by every 2 months or every month this, month that.
But you may not be able to do it because the patient may not come back.
But in the gap in between, you don't have the data. You don't know what is happening, even if the patient comes in. So, yes.
What happens in the situation if you have missing data? Does that person get missed from, like, is it censored out of the study, or do you fill it up with something that you imagine, or do you just exclude it? Like what?
So missingness is a problem, right? Missing data is handled in a variety of different ways. You have mentioned 3 of the ways that people do it. So the one way is to assume, well, first of all, you want to understand why is it missing. And we have, just like we had censoring and informative and uninformative, the missing can be informative or not. Or tick, therefore they didn't come. That's very informative. But if they're missing their CD4 count because they were coming to the clinic and they were involved in a car crash, it's not related to their CD4 count. So it's called at random. And if it's missing at random, you can use methods that can handle incomplete data, like random effects models, or you can, as you say, make up the data. We use a fancy term for making up data. We call it imputation. And imputation is basically making up data under some criteria. How do you make it up? Well, you can make it up in that particular person's case. If, let's say, they're missing their CD4 at month 6, but you have the month 2 and you have the month 8, you can do a linear interpolation. Or maybe correct or not, because you don't know if it goes like that, but you're assuming it goes like that. So that's a linear interpolation. You can do the previous value carried forward. So whatever it was at month 2, and move it. You can take the average of 2 and 8, because now it's not a linear interpolation because you're closer to 8 than you are to 2. But now you take the average of those 2 and you give that one. Or you can say, this person is this age, this sex, this past history of disease, is diabetic, is this, is that. I have 15 other people that are similar to this. What is their value at 2? What was their value at 8? What is this value that I should give? You make a linear regression interpolation. Complex. The problem when you make up data like this is you're making up the data with data that exists in your study. So the overall variability is reduced. This is what people love, because if you reduce the variability, you get bigger effect sizes. But now people say, no, 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 you can't do that. What you have to do is introduce a little randomness to that imputation. How do we do it? We do it, that imputation, with a little fuzz factor multiple times. How many times do we? So we invent the data multiple times and do it 5 times. We have 5 data sets with different values for that person. And now we do the analysis 5 ways and get the average of it. This is a great idea when you have super fast computers to do it. Nowadays, it's standard. 20 years ago, this idea was out there. 30 years ago, multiple imputation. People did not do it because they would do it for small data sets. But now if I'm missing this for this person, and I'm missing the other one for this other person, and I'm missing that for the other person, and now I have so many people missing, how many data sets am I going to do? And if I have lots of missing in other variables, do I impute that? It becomes intractable. People do it, but software has to, and the computers needs to handle. Nowadays, people have the imputation processes and regressions are good enough. They only have to do it 5 times. People were recommending before 20 data sets, but now with 5, the multiple imputation is usually done. But missing not at random is a bias. So if people miss their CD4 because they were had it low, and you're imputing from the other ones, you're artificially changing things wrong. So you have to find out what the bias is. So missing not at random is a problem. And many people ignore it. They just sort of say, oh, I did multiple imputation because it sounds, technically you did fancy statistics. So we did multiple imputation for missing data. When I talk with investigators, I say, do you want to invent your data multiple times? No, I'm not inventing data. We just do an imputation. Imputation is inventing data. It's just a fancy term for inventing data. So just be careful. I always give the advice that one of my professors gave me. The best way to handle missing data is to not have it. It's the only good way of handling missing data. So if you're doing a study where you are the investigator and you are going to be measuring CD4 counts, you make it sure that if the patient doesn't come, you call them, you go and check on them, you go visit them. Don't just accept that it's missing. If CD4 is your important variable, it better not be missing. If you're missing their BMI, but BMI is not an important variable, then don't worry about it. But your key variables, it better not be missing. It's hard to do, it's expensive to do, but what do you do? Oh, because this person had to take public transport to come, and that's why they didn't come. I pay for the public transport because I want to have it not missing. You decide when you're designing your study. If you're doing retrospective studies, you're unfortunately have to pay the penalty of whatever other people did for all it did. All right. Okay. Yeah.
By not having them, you mean censoring or just not including them in?
No. Not having them mean having it measured.
So it can't be a censored thing that you had it till here and then you censor them?
No. This person is missing their CD4 count because it's a covariate. It's not your outcome of time to event. You're not censoring it. It is just missing. The term censoring is for time to event. It's not for having a measurement or not, or having an observation, yes or not.
In a joint analysis, you're talking about a value. So there's a second value that you're looking at. So you're looking at 2 things. This is the CD4 count over there.
Right.
Here's one. You're looking at the CD4 count and you're looking at the chance of death. So you have CD4 count till 3 months or 6 months. And then after that, you have lost them to follow up. So technically, that would be a censored data.
if you've lost them to follow-up, your time to death is censored.
It's censored.
But your CD4 count is whatever you had up to that time point two.
Right.
And so it's not missing afterwards. That's not a problem because you censored the person at their time of death, right? Or time when they were censored. But what I'm saying is, suppose their time to death, they've been there for 18 months and they haven't died, or they die at 18 months. But you're looking at the CD4 counts and they don't have 6. You have 2 and 8, but not 6.
To exclude the patient.
No, you don't exclude the patient. They're missing the 6. If you want to study this, what happened, the path of the CD4, you have to have a value at 6, or you have to make it up. You don't throw the patient out, especially if it's a clinical trial. Anybody that's randomized is included in analysis. That's intention to treat. You don't throw patients out, ever. You have to deal with it. That's why in clinical trials, the primary analysis is usually a time to event. You never have the time missing. Because missing the primary outcome, you'd have to make it up. Most clinical trials always have time to an event. Some of them have, weight change at 1 year, or depression score at 6 months. Well, if they don't show up at 6 months, then what do? Then you have to make it up. And then you have to do the other approach is worst case, best case scenario. And so then people do the sensitivity analysis, saying, well, everybody that missed in the intervention arm, I'll say that their depression was worse by this much. And everybody that was missing in the control arm, I'll say the depression was higher. I'm sorry, was not as low in the other one. So, and then I do the opposite. And if I get the same result, then fine. But if I have many missing, I will get different results. And what do I do then? Possibly commit suicide and not report that study. I don't know. It's because it's sloppily done. If you're missing that, it's because you did not do the study well and go chase the people to get their depressions. And that's why most clinical trials in the health field, they always do time to event. That's why we're doing a workshop on survival analysis, because it's time to event that is the outcome of interest in clinical trials. You don't have that missing. Even if 2 days after they were randomized to intervention, they took that and they said, this tastes like placebo, poof, and they disappear. You still analyze them. They contributed 0 time or 2 days to the study. But that's it. It's not missing. You don't say, I want to know what their status was at 1 year, because that would be missing. All right. So these are 2 examples of this. And this is what we were talking about. Is the dropout informative or not? And if people leave the study, the dependence of both processes on each other requires different methodology. So the repeated measure may be missing if the patient becomes sicker or dies. And so in these processes like CD4 or cognition, the patient with steepest declines may disappear early. And they said, oh, my CD4 is going down fast. The hell with these investigators, I don't want to come back. And they disappear. They haven't died yet, they just drop out. Okay? And so data for the sickest trajectories usually are missing. So we call that informative missing. Or because their kidney function data is missing because they progressed to dialysis. And dialysis was not your terminal event. It was death, your terminal event. So standard longitudinal methods assume missing completely at random. or missing at random, but here we have informative dropout. And so Cox models underestimate the effect of CD4 counts, and longitudinal models produce biased slopes. So the joint model solved this problem by modeling both processes simultaneously. So you have the trajectory of CD4 or cognition as a smooth, continuous patient-specific, and then you have the survival process time to event, and considers the dependence between the two. The hazard at time t depends on the true underlying continuous measure, not the infrequent noisy measurements that you have. And so that's the assumption that is going to be used in the model. So how do they handle the not the informative missing? The survival submodel represents the dropout death process, and the longitudinal submodel represents the biomarker process, and they share the random effects. So hence the model understands that steeper biomarker decline leads to higher chance of death, which leads to more missing biomarker value. And so by sharing of that random effect, they do it. Joint models make them is missing not at random, you can ignore it. That's sort of the beauty of these joint models. The dropout is no longer a nuisance, it becomes part of the model. So the structure is, again, now a little bit more technical. You have the longitudinal model for CD4. We'll be modeling how does CD4 change over time, maybe in a linear way. The survival submodel will be looking at the hazard, and that's that effect of the CD4 on the hazard is put in here. And this is that MIT is the true underlying CD4 at time t. It's called a latent curve. So now we're estimating the latent value of the CD4 at time point t. So those intervening points are now estimated from a latent variable process. A little bit more complicated to get that, but we're not going to explain what the latent curve is. Yes?
I think the predicted count for CD4 for individual patients which have been adjusted in the HIT.
Yep. So it's been adjusted to get the predicted values of CD4 over time, not just at those time points when it's measured.
Given that how good those predictions are will depend on how good your specific model is in the longitudinal one.
How good this is, yep. And so you will want to, you have to definitely correct. You have to have a good model of the process over time of CD4.
But when we design our RCT, that's never the objective. We never design a model in the RCT to have a good predictive value. for the
Right,
outcome.
no, because you will design your trial for the time to event. So this is a secondary analysis that you are doing because now you tell me that you're interested in the CD4 count as well. If you were interested in both processes and therefore doing the joint model in the first place, you would need to specify what is the effect of the CD4 count on the other one. And that I'm not sure has been done. I haven't seen a trial that's planned to do the primary analysis based on joint model. The primary analysis is usually done with the simple template that we've mentioned of the log rank. That's it. This is an adjustment to that would have been done maybe as a sensitivity.
So if I have a secondary outcome, outcome is number of hospitalizations for heart failure, and I'm counting that process, and the tolerant event is death, and I still use the joint model. My interest is to measure the average difference in the number of hospitalizations between the two arms. So
But now your primary outcome is different. It's not time to event.
yeah, it is actually the process.
It's the process. That's different. Now you're now modeling hospitalizations. And now you either have not time to hospitalization, it's a number of hospitalizations in a given period. And if you have multiple periods, maybe it's a Poisson in each period. And so now you have repeated Poissons. It's a whole different analysis. You now How you deal with competing risks, that's, you'd have to think about it. You have a complete different outcome, complete different analysis, totally different design.
So when I'm considering a joint model, the terminal event, the survival submodel is actually the primary one.
Yeah, exactly. The terminal event is the primary. That's why I said that you could have two focus. Oh, sorry. The focus could be on the process of their biomarker or of the measurements over time, or it could be on the survival. But in our case, in randomized controlled trials, most of the time, and for this course, our focus is on the survival one being the primary, not the other. Yeah.
Yeah, because what we are trying to do is the objective here is we have a covariate which has been measured over time,
Right.
and we are trying to see how that covariate has an effect on time to event.
Yeah.
We are not modeling anything for the repeated measures here. Okay, we already have a data where we have a repeated measure covariate. We are trying to see how this process of this covariate is affecting that hazard, which is your time to event.
Yeah. So that's, so what I'm saying is that the data set can be like this. One could be focused on this, or one could be focused on this. Our focus here is this, is a time to that's the primary thing we're interested in.
In the example which I mentioned, where my
It's different.
outcome is the number of hospitalizations, I can do it directly with.
Then you're in here. Your focus is here. But now your time to event is a competing with your hospitalizations, because once you die, now you have no more hospitalizations.
Will I still be using the joint model?
Nope.
I won't need it. I just need the number to be modeled.
Yeah.
Right? By negative, by negative, poison cross or something.
Right.
I don't need the depth.
Right. So the steps to fit this model are you fit a longitudinal mixed model to the covariate or the biomarker. You fit a survival model, and then you fit the joint model by combining the two and sharing the random effects. The R packages, and that's what we'll be showing, run the joint model directly. And this is what we're going to do, that, there's the software for it. But again, your focus is on that time to event outcome. And I think I'll stop there. And we'll have a different example in R. And we can do that after lunch. Questions, comments? Yeah.
So, the multi-state model, I don't think we can use the multi-state model because here we're trying to see covariate is a continuous one.
Right.
I don't think we can convert that to an ordinal
Yeah.
scale. So there is no way we can do a multi-state model if you have a biomarker like this.
And then multi-state models require not only categorization, but having you create the states in a meaningful way that they're mutually exclusive and that they're ordinal. Right? They have to be ordinal as well. You're getting progressively worse. Yeah, but now you're changing the question. You're changing the research question, which is fine. I mean, so all of these things you can do, but again, depends on your research question, what you're doing. Our focus in this workshop is we're interested in the time to an event outcome. Now we have this other process that is related to this and is related to the outcome. And I want to jointly study them, but my focus is still on the time to event.
You just give us one more example of the survival and longitudinal submodel, exactly what they mean, just once more.
So the longitudinal submodel is modeling
The time to event.
no, it's
The-
modeling the biomarker.
Biomarker.
For the CD.
And the survival is the
Is modeling the time to event.
time.
So basically the two models are, one is the process you're trying to find out with the CD4, how the pattern is, whether it's increasing or decreasing. So you're taking that increase or decrease in terms of the beat parameters, and that is what you're incorporating as one of the covariates into your time to event model. Ideally, I mean, just in the layman term.
Yeah, so layman's term, that's what
Yeah.
you do.
That's why you're capturing the process of the CD4 change on the time to event, which is your outcome. Yeah.
Maybe this will become clearer in the example in the afternoon. Yeah, show the CD4. Okay.